Hello everyone, today we present our latest work in CVPR 2025 with title CL-LoRA, Continual Low-Rank Adaptation for Rehearsal-Free, Class-Incremental Learning. This work focuses on leveraging pre-trained models for continual learning instead of training from scratch. Today, using pre-trained model has become a common strategy for most machine learning projects due to its rich knowledge and strong generalization ability. Also, the emergence of large models with even billions of parameters further improves the performance on downstream tasks, but it also requires a huge training cost. In this work, we are interested in using pre-trained backbone for continual learning, but only fine-tune a small part of parameters to make it more scalable towards real-world applications. The key challenge here is maintaining both adaptivity and generalizability through parameter-efficient fine-tuning. In this work, we are particularly interested in low-rank adaptation, LoRA, a popular parameter-efficient fine-tuning strategy. Suppose we have a pre-trained backbone with parameter W. Instead of fine-tuning the entire model, LoRA decomposes it into two trainable modules, a down projection matrix B with dimensions D times R and an up projection matrix A with dimensions R times K. The value of rank R is much smaller than D and K, typically is just 5 or 10. Thus, the total trainable parameters is much less than original model. While this still achieves competitive performance compared to fine-tuning the entire network. In vision transformer architectures, LoRA is typically attached into the multi-head self-attention layers in each transformer block. In this example, LoRA is added to the pre-trained query and value matrices. So the question here is, can we adapt LoRA for continual learning? Assuming we only use one LoRA to learn n tasks sequentially, similar in conventional continual learning, the LoRA also faces catastrophic forgetting issue where it forgets previous knowledge when learning new task. A simple solution of this is to initialize a new set of LoRA for each new task, as shown here. This is exactly what most recent frameworks did. However, it also comes with the limitations. Firstly, it requires significant computation during inference using all the learned LoRA modules. In addition, since each task-specific LoRA is learned independently, it also loses valuable inter-task information, result in suboptimal performance. In this work, we introduced a novel dual adapter framework. Given a pre-trained vision transformer with n blocks, instead of learning task-specific LoRA for each new task, we replace the first L blocks with task-shared LoRA modules that are learned continuously without reinitialization. The idea of this design is simple and straightforward. Use task-shared LoRA to capture cross-task information, and use task-specific LoRA to learn task-unique knowledge. Our design of task-shared LoRA is slightly different from original LoRA, where we use frozen random orthogonal matrix as down projections, which effectively preserves the input feature and alleviate forgetting since the parameter is not being updated. For training, besides the regular cross-entropy loss, we propose the knowledge distillation with early exit to avoid forgetting in task-shared LoRA. This step is further enhanced by gradient reassignment where we prioritize the retaining for most important weight parameters. Finally, to enforce learning of task-specific knowledge, we apply an orthogonality regularization among all learned task-specific LoRA modules through learnable weights. For inference, we leverage a prototype-based classifier. Instead of learning the class weights through gradient optimization, it uses the average features extracted from training data using the corresponding LoRA as classifier weights. Then, given a test image, we extract the corresponding features, compute cosine similarities, and concatenate them as final output logits for prediction. This prototype-based classifier effectively preserves pre-trained knowledge and also avoid the optimization bias in classifier. We compare our method with existing work on multiple benchmarks and show impressive performance with minimal computation overhead. We also explore the effects of task-shared LoRA in detail. We first change the position of where we insert the shared adapter, and we observe that performance improves significantly when L increases, validating our core motivation that incorporating task-shared adapters helps leverage cross-task knowledge to obtain better performance. However, the performance degrades when L becomes too large, particularly when all adapters are task-shared. These observations demonstrate that both leveraging cross-task knowledge through shared adapters and maintaining sufficient task-specific capacity are crucial components for effective class-incremental learning. Finally, we also show the scalability of using task-shared LoRA by comparing required number of adapter forward passes for each test data during the inference stage, where our methods significantly reduce the inference cost while achieving improved performance. The source code is available on GitHub, and feel free to send email if you have any questions about this work. Finally, there are multiple fully funded PhD or research interns available at Indiana University Bloomington, Department of Computer Science. Please send your CV if you are interested. Thanks for your watching.